Okay, welcome to the next video. Here we're going to learn how to solve for x. We've just finished going over PEMDAS and the order of operations. That was useful for simplifying an expression. Now we're going to be looking at equations, which has an equal sign and something on both sides. So here we're trying to work backwards to find out what the value of x is before all these modifications or changes have happened to it. So when we work backwards, we're going to go in the opposite order of PEMDAS. We'll start by undoing the last thing that happened, and the last thing that has happened is the addition or subtraction. And then from there we'll go and undo multiplication and division. Finally we'll undo exponents, and very last we'll undo the parentheses and go inside the parentheses. So instead of doing the parentheses first, we'll be doing the parentheses last. So in order to do this, we have to follow the golden rule of solving equations, which is whatever you do to one side of an equation, you must also do to the other. So you can do anything to the two sides of an equation as long as you do the same thing on both sides. Now, once you've chosen what you want to do to both sides, whether you're going to add 5 to both sides or divide by 3 on both sides, or whatever that step is that you're going to do, you still have to follow PEMDAS individually on one side and then individually on the other side when you're going through that process. So let's start off with some examples. If you have 2x plus 5 equals 8, if you look just at this side of the equation, you can look at this variable x and ask yourself what happened to it. So first, it was getting multiplied by 2, and then it was having 5 added to it. So if we want to work backwards and undo those changes, the first thing we need to do is subtract 5. And if we subtract 5 on this side by following the golden rule, we also subtract 5 on this side. And then I typically show it here, and then cancel out whichever one cancels out, because the whole point of doing this is to cancel something out. Draw a nice line so you can separate this part of your problem from the result. And what's left here is 2x equals, and then 8 minus 5 is 3. Okay, now, whatever number we had x, it was being multiplied by 2, so to figure out what it was before that, we have to do the opposite of multiply by 2, which is divide by 2. Again, we show it on both sides, cancel that out, and our final answer is x equals 3/2. So we're following PEMDAS individually on one side when we simplify, but we're following the golden rule. Whatever we do on one side, we have to do on the other side overall, and we're working backwards, the opposite of PEMDAS. Let me look at this problem real quick and show you let me show the same problem again. 2x plus 5 equals 8. Now suppose that you wanted to divide by 2 first. Okay? Technically, you can actually do that. Like I said, you can do anything as long as you do it properly. So if you want to divide this by 2, the trick is that most students will make a mistake on is they'll only divide this part by 2. But the golden rule says whatever you do to one side, not to one piece. So it's one side and the other side. So if you've selected divide by 2 as your operation, it's okay, you can divide this side by 2. But here, you can't just divide by 2 right here. You have to divide the entire side by 2, okay? Which means you're dividing this part by 2, the 2x over 2, but you're also dividing the 5 by 2. And so, because that's going to leave you with, so let me kind of separate here. That will leave you with 2x over 2 is just x, plus 5 over 2 is a fraction. There's nothing necessarily wrong with doing it like this, but because it leaves you with a fraction, your next step might be a little bit harder. And if you have a more robust problem with lots and lots of steps, if you do them out of order, even though technically it's okay, you'll end up creating a lot more work for yourself. So by working backwards in the opposite of PEMDAS, you will undo those operations in a nice methodical way that will make the problem pretty straightforward. Okay, let's look at another example. Okay. Now, when you look at this left-hand side, you notice it has a lot of stuff in it. So before we start applying the golden rule, like, you might think, oh, let's add 1 to both sides to get rid of this one. But it's a lot easier if you first combine like terms or simplify this expression as much as possible by following PEMDAS. So here we have a 4x plus x minus 8x. So we're adding and subtracting. We can combine like terms. 4x plus x is 5x, and 5x minus 8x is negative 3x. When you're adding and subtracting things with variables, all you have to do is add or subtract the coefficient and keep the variable the same. So think about x as like an apple. 4 apples plus 1 apple is 5 apples. And if you have 5 apples and you try to take away 8, you'll have negative 3 or you'll owe 3, something like that. Okay, so that's gone, and gone. Now we have a positive 3 and a negative 1. So that's 3 minus 1 is 2. And then on this side of the equation, there's nothing to combine, so we just have a 15. Alright, now we've got it simplified and it's much easier to solve. So the first thing to do is work backwards again, so we'll subtract 2 from both sides. Those cancel. We have negative 3x equals 15 minus 2 is 13. And the last thing we'll do is divide by negative 3. Divide by negative 3. And you should really show each step on both sides of the equation. That will really help you prevent mistakes and make it easy to follow your work and see what you've done. So these will cancel out. So we have x equals the negative sign. If you have a negative in your answer, it's typically best to put it either in front or in the numerator, not leaving it in the denominator. And 13 over 3 does not reduce. So negative 13 thirds is our final answer. Okay, a couple more examples here on the next page. Let's take a look at this one. We have some choices. When we start with a problem like this, we could start by working backwards, or we could start by simplifying this side of the equation. So if you wanted to simplify this side of the equation, you would totally ignore this equals 12, and you would just zoom in on this part. And let's try that. If you wanted to simplify this side, you might distribute the 3, and that would give you a 3x, and then 3 times 4 is plus 12 minus 5 equals 12. Then you could combine the 12 and the negative 5, and you could get 3x plus 7, because 12 minus 5 is 7, equals 12. And now you've got it simplified all the way down. You could subtract 7 from both sides, which gives you 3x equals 5, and then you could divide by 3, and you could get x equals 5 thirds. That would be one pretty good way to do it. Another way to do it is to start by adding 5 to both sides. So if you try to do that, you can do plus 5 plus 5. That would give you 3 times x plus 4 on the left-hand side equals, because those cancel, 12 plus 5 is 17. Then you could divide by 3. Notice I'm not going inside the parentheses, because when we work backwards for PEMDAS, parentheses will be absolutely last. So you can't subtract 4 right here because it's inside the parentheses. This 4 right here is actually being multiplied by this 3. So the number, even though it's a 4 right there, it's being modified by the number outside the parentheses. And so if you tried to go in there and subtract 4, you'd be breaking the order of operations. Okay. So we divide by 3, and now we have x plus 4 equals 17 thirds. And then the last thing we need to do is subtract 4, and we get x equals 17 thirds minus 4. 4 we could write as 12 thirds to get a common denominator here, and 17 minus 12 is 5 thirds. So which of these methods do you think was easier? Option 1 was to distribute and simplify this side of the equation first, and then solve. Option 2 was to start solving right away. So which one is easier? It kind of depends on your personal taste and how you like to solve them, and it also depends on how the problem is set up. Let's look at another example. Okay, 5 times x minus 1 equals 10 times x plus 2. Here we have variables on both sides of the equation. So anytime you have variables on both the left and right side, you need to combine all the variables together on one side of the equation and all the numbers together on the other side of the equation. So we could distribute the 5 in here and the 10 in here, or we could notice that 5 and 10 are divisible by each other. So if we divide this side by 5 and we divide this side by 5, these 5s will cancel, leaving us with just x minus 1 here, and the 5 and the 10 divide and give us a 2 times x plus 2. Okay, now I can distribute this 2 in, and I can get x minus 1 equals 2x plus 4, because 2 times 2 is 4. Now I need to get all my x's on one side and all my numbers on the other side. So I could move this 2x over to this side by subtracting 2x from both sides, or I could subtract 1x and move this x over here. Since it's nice to have your final amount of x's be positive, because you don't want to, I don't like having negative numbers, it's easier in my opinion to subtract x from both sides. So these will cancel out, these will cancel, leaving me with negative 1 equals 2x minus x. So 2 apples minus 1 apple is just 1 apple, plus 4. And now to get x by itself, I can subtract 4 and subtract 4. Those cancel, leaving me with x equals, over here I have negative 5. And notice at the very end I've switched it so that my x is on the left and my answer is on the right. If I have negative 5 equals x, I can simply change the order and write 5 or x equals negative 5, and it doesn't matter. So to summarize, you're going to solve an equation which has something on both sides of it by getting all of your variables together on one side and everything else away on the other side. You can do that by following the golden rule. Whatever you do on one side, you have to do on the other side. And make sure you're doing it to the entire side, not just a part of that side. And lastly, when you're simplifying one side by itself or the other side by itself, then you do follow PEMDAS when you're just simplifying an expression. All right, good luck when you're working on these problems.